that has the property that it twists modules and it twists intertwining operators. So in particular, since we have the trivial intertwining operator from v and v to itself, then twisting by it already gives at least some. So at least we get a family of examples. These are not the most interesting ones. They are not the most general one, but they are something. They are something as long as you are able to find such delta operators. And the lemma we concluded with in the last lecture is the statement that, well, at least if my vertex algebra has a Heisenberg subalgebra, a free boson subalgebra, for example, which every affine vertex algebra has, it has a Heisenberg subalgebra associated to its Cartan subalgebra, then you have such a delta operator. And it satisfies all the desired properties. And this statement holds for any alpha here. If you now want to twist a module of a larger VOA where the Heisenberg algebra is a subalgebra, then being in this larger VOA will give you restrictions on this alpha, but only there. So that was one question that appeared at the end of last lecture. So now...
So did you just say that I mean, here the hypothesis was just that there was a subalgebra, but then the conclusion was for every...
So this is a statement about the delta operator, right?
Yeah.
So, and
I mean, it is surprising that all the computation just happens in the Heisenberg.
Oh, right. V in the subalgebra. Right. Very good. You're always looking very carefully at it. So there I have to write pi for, yeah.
So also in the 4 then, I guess.
Also in the 4, exactly. All right, yeah.
I don't know.
No, this actually holds for all v and v. Okay, I have to go over the proof, but I'm pretty sure that I didn't use the subalgebra property here. Let me have a... Yeah, here v is correct. So, okay, good. But now let's take the special case where our vertex algebra is just.
That's a quite strange statement. Why should it be true? But that's a quite mysterious statement because the calculations you did at the board, they only involved pi, and now you're making an expression for some a priori much bigger thing. Why?
Yeah. Well, you have this much bigger thing, which is naturally a module for the Heisenberg algebra, and the statements that the proof only needs that you have a module for the Heisenberg algebra, so it works on any module. Okay, now anyway, let's see on what is the twisted module. So let's restrict to the case where our vertex algebra is just the Heisenberg algebra, and let's see how our delta operator.
I'm sorry. What is the hypothesis of this lemma?
Okay. The hypothesis is that we have a vertex algebra that has the Heisenberg algebra as a subalgebra, and this Heisenberg subalgebra acts semi-simply on it. I think I want to use that.
And do I know what it means to be a sub-vertex algebra?
I haven't introduced that. That's correct. It's a subvector space that itself inherits the structure of a vertex algebra.
Means when you apply the fields,
Yeah, right.
it
It's,
stays in itself.
yeah. So here, right, we have a vertex algebra that contains the vacuum Fock module of the Heisenberg algebra as a subspace, and moreover, the fields corresponding to this subspace give a vertex algebra structure on this Fock module. Right, it's the natural thing. Okay. So let's see what was the delta operator. It was this z to the alpha x naught, but x naught, the zero mode, acts just as zero on the whole vacuum module, so I can ignore it. And then this e plus was the exponential of this this power series in the positive modes of x, and all positive modes annihilate this except the one mode. So that means this whole huge exponential truncates to two terms. Right? So that we have the identity, of course, and then the only other term that acts non-trivially is this one. And so we get our vector back. And now the commutator of x1 with x minus 1 gives us just 1. So that means we get plus alpha. Okay, now let's go on. What is the action of the Heisenberg, of the field corresponding to this vector on the twisted module? It is the action by the delta operator acting on this vector. Right, this is the definition of the action. And now we can just insert what we computed.
What happened to the term z to the x0? What happened to the term z to the x0?
Yeah, x0 acts on the vacuum. It doesn't contribute.
But it's on the left.
Yeah, and it commutes with everything, right? Because the commutation relations of the x0 commutes with everything, right? If n is equal to 0, you always get 0. Okay, good. So I insert what I just computed and use linearity.
Before you had all kinds of different z's, and now there's only one z.
Yes, because now I'm just whenever I'm interested in a product of fields, I have more than just one z. So, for example, for the property of the duality properties, we're always involving two fields, and I can't insert them at the same point. But now I'm just interested in the action of one field on a vector, so I only need one variable. Okay. Now here we can use linearity, so we can just take alpha z inverse out.
I'm still confused. Why is, I mean, the thing you're allowed to put in the y is a priori element of v, not an element of v with some power series.
So you're confused about the z inverse here?
No, I'm confused about delta. I mean, the thing you've inserted in there is some field applied to x.
Mm-hmm.
And that's an element of v bracket z, right?
This one here, yes. Mm-hmm.
And so before, like, the definition of the y was allowed to feed into it elements of v.
Right, and now I extended to also allow to insert power series in Z. But I already did this implicitly, I mean not implicitly, explicitly in the duality. This associativity statement had the same type of problem.
Yeah, but now you have the Z in there, and you have the sum over that Z, and you have another Z.
Yes.
This doesn't cause any kind of infinite problems because...
So in this case, this doesn't cause any problems because of the property of the delta operator, right? You see it's only polynomial, so there's no possibility for a problem. No, of course you have to be concerned about this issue, but here there's nothing to worry about. So we do this computation and just insert the action of the delta operator on this vector. We use linearity, and here we use also linearity, and that the vertex operator to the vacuum is just the identity. So this means on this nice vector, the action of the the twisted action of the vertex algebra on the module is just the ordinary one plus this additional term here. So it's you see it gets modified in a very mild way. Okay, and it should be, because what do we expect to happen here? We started with a vacuum Fock module of the Heisenberg algebra. We get a module that has isomorphic underlying vector space. So it must be a Fock module again. So all that can possibly change is that the highest weight, really. And what should it change by? We would certainly expect the weight to be related to alpha somehow. So let's just define. Let me just give it a name, this new field. And that's a field on the twisted module, and so it has an expansion in terms of modes in the usual way. And we see that what are these modes now? Surely we look at this and we see, no expansion coefficient changed except the coefficient of Z inverse. So this means we get x is just at xn, and the coefficient of Z inverse corresponds to the zero mode, right? Z inverse we have here if n is equal to 0. So we see, this x tilde alpha is the ordinary x, except that the zero mode gets shifted by alpha. Now let's look back at the definition of the Heisenberg algebra. And now if I asked you find automorphisms of this Lie algebra, x naught is in the center, right? And it never appears here on the right-hand side. So I can, of course, change a central element by my favorite scalar, and the commutation relations stay the same. So this here is a very trivial automorphism of the Heisenberg Lie algebra. Everything non-central I keep unchanged, and just the central element I change by my favorite scalar. What's the effect, right? All of a sudden x naught doesn't act on a vector by its eigenvalue anymore, but this eigenvalue gets changed by alpha. So so it's actually, Gabriele, it's really good that you asked your question, because you see in this example very nicely that this delta operator in the example of the Heisenberg VOA very explicitly realizes this admittedly fairly trivial automorphism of the Heisenberg Lie algebra. Okay, and so that means let me now write down the So this means if I, so recall that by pi beta I denote the Fock module of highest weight beta, and I just repeat in words what I mean by it. It is the module generated by a highest weight vector on which x naught, the zero mode x by multiplication with beta, all positive modes act as zero, and then you induce. So that's what it is. So and now what happens if I twist this Fock module with the delta alpha operator? The underlying vector space is the same. The xn act all of them in exactly the same way, except that x naught doesn't act by multiplication with beta anymore, but by multiplication with beta plus alpha. Very good. So we get that the twisted module of this Fock module, by which I mean I take the underlying vector space, but the BOA action is not given by the original one, but the one twisted with the alpha delta operator, is the Fock module of highest weight alpha plus beta. So in particular, you can take the special case beta is equal to 0, just your VOA itself, and by just doing all possible twists, you get all possible Fock modules. You maybe have gained a different perspective. Okay, let me now in general. So that means if we have that the Heisberg algebra is just a subalgebra of V, then we can also look at the delta alpha twisted module, which I always like to use this notation for it. It's quicker than this one. Then the twisted module is a V module what could possibly fail. The only thing that could fail here is the first condition. If and only if, and it's really an if and only if this condition A holds. In other words, it means the V module. It means not the V module. V itself is Z graded by the operator alpha times x naught. Okay. One more comment. If this one doesn't hold, you still get something that you could consider nice. It's called a twisted module. It also plays a role in many things. Locality is violated, and so that's in many respects it's less nice. It's a particularly important if you study something that's called orbifold theory, but we haven't touched that yet. So for example, if we go back to SL2, we have a Cartan subalgebra in there generated by the field corresponding to H, and E and F have H eigenvalue 2 and negative 2. That means V is 2Z graded by even integers by x naught. So that means as long as I take alpha to be a half an integer, this condition is satisfied. And if I, and of course I think about half integers, I naturally think about this as the weight lattice in that setting. So, or co-weight, I should better say, if I want to think about non-simply laced in general. So, and in fact, that's related to Gabriele's question. So, if you have a module of the affine Lie algebra, then for any element in the for any any element in the Cartan subalgebra, you can do such a possible twist, but this integrality condition is satisfied if and only if this element in the Cartan subalgebra you can identify with a co-weight. And that makes sense because co-weights are exactly the translation group of the affine Lie algebra is exactly is given by the co-weight lattice. And the spectral flow automorphisms that I have sketched for SL2 due to your question are exactly those automorphisms that come from translations of the wild translations that correspond to the co-weight lattice. So in some sense, we have rediscovered it from a VOA setting. Okay.
Excuse me. This is somehow, I thought the issue was that you get a Laurent polynomial instead of a series. But now you're saying the issue is that I get a non-integral power of Z.
There are always different issues. So the point is this delta operator is simply nice, full stop. All right? And if it's nice on the Heisenberg algebra, it still stays in many respects nice on the bigger VOA. However, one thing that can fail is that, so this delta operator is this Z alpha x naught times this E plus. This E plus behaves nicely no matter on what I act. It's just a nice thing. But this one acts, of course, by Z to the alpha times the eigenvalue of x naught. So that might not be an integer, alpha times x naught. I mean, alpha times the eigenvalue. And if that is not an integer, then I have a problem with this integrality condition. And when I have a problem with this integrality condition, then I have a problem with locality. Locality will simply not quite hold. And so I simply don't get a true local VOA module.
But you answered then somehow in relation to integrality as opposed to why is it Laurent series?
The why Laurent series? No. Laurent series is here. Now you're confused with this statement. Is that what you're asking about?
Well, before I understood that the point of the first line was to say I get a Laurent series rather than a general,
No, the point was you get a polynomial.
Now you're saying.
No. Right. No. The point was you get Laurent, or the point is you get something in Z and Z inverse. That in fact is even polynomial in Z and Z inverse. All right. And if this Z grading condition fails, then you would get, so in general you get something in Z alpha lambda if lambda is the eigenvalue of x naught. So this might not be an integer, and then you wouldn't like that. It would imply that locality fails. So.
But it's just that.
Why would that imply that locality fails?
Because the action is not in terms of integer powers of Z. And if it's not in terms of integer powers, I
agree that yesterday and the day before yesterday we only had integer powers.
Yes, because we were always talking. No.
Powers, and it was never said that this means locality fails.
No. Right. No. So.
Anyway, maybe we should just go on.
You're just confusing yourself, I think. But you can also, I mean, I simply have this lemma, and clearly, I mean, the point is if V is Z graded by this operator, then this lemma extends that I can replace this pi by a V. If that fails, I can't do that. So that means the lemma doesn't apply.
It was only about for V and pi. Now you're applying it for V not in.
Yeah, and for that I have to make sure that all four conditions also hold for the bigger VOA. B, C, D, no problem. A is the problem to extend it to a bigger VOA. That's what I'm telling you. Yeah, and A is not a problem because here of any polynomial condition. It is the power. You need integer powers. That's the problem. And that problem arises only because of this prefactor. But it's a serious problem, so you don't get a module.
I don't understand why you say it has a locality failure.
It's
to me, like, you wouldn't even define the thing that
you wouldn't even have an integer, I mean, an action in integer powers. It just doesn't make sense. So.
No, but I guess the question, and that's the one I had, was that, you know, V is set graded by alpha x0. This has to do with that there's no sort of non-integer powers, but
Yeah.
the fact that it becomes Laurent polynomials is stronger, isn't it? It does not follow from the fact that V is C graded by alpha x0.
No, yeah, but let's maybe go on because we are talking here about a small subtlety. It's
I was just trying to understand. You said i.e. V is set graded by alpha x0, and I was thinking, oh, how does that imply Laurent polynomial? But it doesn't actually.
No, it just all it means is this condition holds if and only if V is Z graded by alpha x0. So, but I should have. I wanted to explain this better, but I can also. So these two conditions are actually equivalent.
I think that's his complaint, that they're not equivalent because the bottom one shouldn't imply the first one. Because saying that it is a polynomial feels a lot stronger than saying that it is graded by alpha x naught. Maybe they are equivalent, but it's not obvious.
Okay.
Exactly. That's what
Okay. Now. Okay. I misunderstood your question. Assuming all the rest holds, then this statement, this single statement. I was only talking about the statement relevant for our lemma to hold.
They don't, but it's under this assumption.
Under that assumption, absolutely. I was only talking about what's important for the moment. Okay.
So should we think that this is a condition on alpha now?
Yes.
We just have to move alpha.
Yeah, absolutely. It's yeah.
Thank you.
It's so you should think about it. A vertex algebra has a Heisenberg subalgebra, maybe not of rank 1, maybe corresponding to a higher rank Heisenberg Lie algebra. For example, SLN, or I mean just a simple Lie algebra, it has a Heisenberg subalgebra corresponding to its Cartan subalgebra. That means it's naturally graded by that, and in fact it's naturally and what are the weights that appear? They lie in the root lattice naturally, right? Because the eigenvalue of I mean the action is in the root lattice, and so then that means it's for an affine vertex algebra. It says this twisted module is a module for the affine vertex algebra precisely if alpha is in the dual lattice of the root lattice. So it's a coveight. Good. Let me state a theorem. We have a map from the space of intertwining operators of one type. We would like to have some kind of commutativity. So we would like to be able to compare intertwining operators where I interchange the role of M1 and M2, and that is called skew symmetry. The image of the intertwining operator is defined by, so I assume this vector to be homogeneous just to get this sign. And now you need again the Virasoro algebra. And now here I have to take a choice of -1. This R is just labeling a choice of -1 here, because remember this intertwining operators are arbitrary powers of Z appear, so I can't just write -1 here. I have to write e to the pi I or e to the negative pi I, something like that. And M2. And the statement of the theorem is that this is an isomorphism on the spaces of intertwining operators. With inverse omega negative r minus 1. So I'm saying this without any further comment. This is called skew symmetry. It's the intertwining operator of type M1, M2, and M2, M1 are related by a very explicit formula, which is of course nice. It involves this action of the Virasoro -1 mode, and it involves also to replace z by minus z in this sense here. Okay, now with this theorem we can do a computation of fusion rules, and fusion rules is something especially in physics literature one hears quite a lot. So the fusion rule n with index 3 modules is equal to the dimension of the space of intertwining operators of the corresponding type. Right, this is here was the symbol for the space of intertwining operators of this type, and fusion rule is this dimension. So these are non-negative integers, and determining it gives you some kind of information about these dimensions of intertwining operators. One can also identify them with the dimension of conformal blocks on the sphere. So conformal blocks at some point become interesting. Let's see what we can do. So let's do a computation. So let lambda be a complex number, and what do we have? We clearly have that that there is only an intertwining operator of type Heisenberg VOA to something if this lambda is equal to 0, right? We have the vertex operator you only have an intertwining operator of type VV something, with something is the vertex algebra itself, or a module that has V as a submodule. Okay, and now, what did we prove is that this here is the same as the dimension of intertwining operators of type pi alpha, pi lambda plus alpha, because if I have an intertwining operator of such a type, then I can twist it by spectral flow, and the effect is that you twist this module and this module in the same way. Well, the spectral flow twist of the Fock module is the Fock module at highest weight alpha. The twist of this Fock module is the Fock module of highest weight lambda plus alpha. Okay, what else can I do? I can apply this theorem. This means I can swap the first and the second index. Right? It's just this. It's applying the statement of this theorem. What can I do next? I can again apply the statement that is the spectral flow over delta beta operator, and now maps an intertwining operator of this type to an intertwining operator of type pi alpha, pi beta, pi lambda plus alpha plus beta. right? And this holds for any alpha, beta, and lambda. And so this means I quickly have computed what the fusion rules of the Heisenberg VOA are.
Excuse me.
Yes?
So, I really don't understand how do you define the dimension of type n1 and n2?
Dimension is a vector space.
What? You mean, so here you don't denote the linear map, you denote the VOA, right? Here you mean the dimension of the VOA, right?
Where?
That is, you define the fusion rule.
It's the dimension of the vector space of intertwining operators of type M1, M2, and M3. Right? So this is a linear vector space. Right? And so on the VOA itself, the only intertwining operator you have is the VOA action on itself. So it's one dimension.
Well, N1, N2, N3. Yeah, I see. Yes.
Yeah, good.
Always assume they are vectors.
You can always ask me afterwards more, right? You have a question?
You mentioned that modules don't necessarily have dimension, but
No. But actually, I also want to. You're asking a lot, and I want to come to most of it. You have a question as well?
That complex number C there, should that be there? Because we're comparing numbers, right?
Right. Yeah. No. Right. In my old version, I had the vector spaces themselves. Thank you. Yeah. Okay. So the corollary, we get that the fusion rule pi alpha, pi beta, pi gamma is equal to 0 almost always, and it's one-dimensional if gamma is equal to alpha plus beta. So somehow a nice statement, right? And let me also give you the general statement is very similar, and that's also quite a nice statement. The same type of statement applies if the Heisenberg algebra is just a subalgebra of a general VOA. So in general, we have the statement we have the statement that in general, we have an analogous statement.
Sigma star V.
Hence, absolutely. Right. Okay. Now I want to do an exercise with you, and namely I want to compute the number 1 again in a different way.